Good morning. I'm Oliver Gao. I'm the Cornell System Engineering Program Director. I have been very fortunate to conduct what I call the system conversations with the great speakers that we bring to Cornell campus. So today I'm very delighted to welcome Dr. Feng Qiu. Actually, Dr. Qiu, he is the principal computational scientist at Argonne National Lab, which we all know they do wonderful work, in helping us dealing with, systems challenges facing us in the energy systems. So, Dr. Chu, welcome to Cornell. First of all, I think, as I mentioned, the Argonne National Lab plays a very important role in helping the country and the society address key challenges surrounding energy systems, right? Actually, a lot of DOE energy labs they do that. But I think one thing that is very unique there at Argonne National Lab, in interaction with many people, I found that you are really building an intellectual power of computation, and you are really combining, the computational and even system analytics with all these, energy system challenges. So, of course, before we go to, your area of computational optimization, I just want to ask you to help give us a bigger picture of, the energy systems that our societies are now, working with, and also what do you see as the key challenges that are facing our energy systems? Because as you mentioned, you are the section lead of energy system division. So dealing with energy system challenges. So what do you see as the key challenges facing us?
Yeah. So I think in general there are many challenges. Not only from the technological side, but also from the management operational side. So from the technology side, the battery technology, storage technology, smart grid technology, all this kind of hardware, inventions that still need to improve. For example, the battery need to be, storing more power, have longer recycle time, and so that's a hardware side, right? But from the operation and running the grid, it also has been challenged, especially in this computational challenge. So my expertise is from the computational side, so I can make more comments from this side. So basically, when I was first becoming a postdoc at Argonne 10 years ago, and people were questioning me, why do you go to the energy research? It's a dying industry. Like if you look at 10 years ago, I think even for the power system of faculty position, it's very few. And people saying this industry has been developed for decades, right? Everything seemed to be ready. It's not a big deal. Why we need so many people look into that, right? So that's a decade ago, 10 years ago. So
what did you find out in the past 10 years?
Yeah, that's quite interesting. So I mean, part of the reason people make this comment that because they look from outside. If you look at outside, yes, it is many of these technologies that are being advanced are not entering people's life right now. But it's very important. And the other reason is that maybe 10 years ago, 15 years ago, the grid has not been as challenging to manage as today. For example, the renewable energy, you have seen in the past decades, it has been aggressively integrated. And EV, right? EV is, I think this is recent 5 years, right? Since Tesla and other manufacturing start, pushing out, the government just start subsidizing, this EV things. And decarbonization, right? So these are all very recent topics. Energy justice, how do we, get everybody, equal access to energy, So there are a lot of challenges, and also like recently you have this energy security, right? Like supply chain, the disruptions, to the energy supply. So these are all coming out maybe in the past decade. I mean, there are many things like happening before, but people just don't realize that. So once I start working in argon, so start really looking into. So by training I'm an industrial engineer, so I don't know much about energy. I don't know power flow equations how to write down at that time. But when I start doing that, I gradually feel like the focus are shifting. But one thing has not changed is that the need for computational advance. Like just take a simple example. After deregulation of the power markets, maybe 15 years ago, so all this demand and generator supplies, they go to a market to clear, decide who is going to produce and how much is the price, right? So we have a couple of power markets in U.S. So one of the key challenges there is that they need to solve a big scheduling problem. So this scheduling problem decides the efficiency of the system, the pricing, everything. So that problem is a mathematical problem called the security constraint unit complement. So that single problem are clearing the power markets in U.S. alone, total $400 billion every year. So you can imagine that the whole system efficiency depends on that single mathematical problem. So we can say like the computational investment are so critical because every fractional solution quality you improved for that problem indicate you have hundreds of millions of potential savings for the whole U.S. market. So that's a lot of people are trying to advance the computational technology. So that's only part of the whole picture, and you also have like some other mathematical problem that ensure that the system is run securely. Require a lot of simulation technology and also protection, and also recent years you have a new energy component that come into the picture. For example, like the distributed energy resource. You have aggregator as a new business model, right? And also you have a large amount of energy storage coming to the grid, right? And a combined cycle. So all these things just significantly build up the computational challenge in the past decade. So, with this speed of complexity increasing, it is very challenging just in the near future. Because some markets are quite small. They haven't seen this yet, but for bigger markets, such as the MISO, PGM, they start seeing this. For example, they want to run into 15 minutes energy scheduling, but it is very challenging because hourly unit commitment is already challenging enough. We haven't, built up the full-blown model yet. So you can see there's a lot of demand for the computational advance in this energy field. So this is only just one single problem, and you can think about like, how do we effectively put the EV charger, right? How do we deploy the distributed energy resources? There are so many things are just coming up that we haven't paid enough attention before.
That's thank you, Dr. Qiu, and I think that's wonderful. I feel from what you just shared with us, of course, you discussed those key challenges that we're facing with the current energy system, and also you pointed out the potential power of optimization and system modeling that can play a role in addressing those challenges. Kind of one side is a challenge, and another side you offer some potential ways for us to approach those challenges. But from what I heard from you, apparently you started from the hardware, right? You talk about technologies. But I think you concluded towards the end of your just what you shared with actually you concluded by pointing out the real challenge is really the system complexity. I feel somehow of course you mentioned you started your postdoc at Argonne maybe 10 years ago, and also somehow I think your conversation just kind of shared how your mindset and how your knowledge structure evolved. Kind of from, and assume that when you, as you mentioned, you were trained as industrial engineer, and you were equipped with all those optimization techniques and algorithms, and you know how to solve the most complicated optimization model if that model is formulated correctly. But apparently now what you are dealing with is that you are not only solving those optimization problems, actually one key thing is how you can formulate those optimization problems to take into account, for example, energy security. And of course, you also mentioned energy equity, which is, I feel, probably even harder to address, right? So now let's kind of, I want to get us to a little bit to kind of, the optimization model formulation. Because especially now at your level, I feel you probably agree with me that model formulation is more important than just get the model, get the problem solved, right? Because in most of the PhD training, people are trained to be very good problem solvers, but they don't know how to define a problem. And actually now when you, from your work, and actually sometimes you realize actually defining the problem and formulating the problem right is way more important than solving the problem right. So kind of are you solving the right problem or are you solving the wrong problem right? Right. So that's very important. So in that case, kind of, so now as you are coming across all this system complexity, so tell us more about not the system challenge, but the challenge like when you are trying to formulate, when you're trying to translate a real world, like for example, Argonne National Lab, when you take over some task from the DOE or from the society, and of course in the end, you will translate all those things into mathematical problem. And then of course, that's not enough. After you get the solution from those mathematical problems, you want to map the results from your mathematical problem back to the societal issue. So through this kind of thing, basically my approach, I want to kind of first, from the model formula, and later on we're going to dive into how you solve those problems. But I want to start with, so what challenge, what issues did you cover? For example, let's say, electrifying transportation. You mentioned the EV, right? It seems like now, even in the Inflation Reduction Act, actually there is a lot of climate change component embedded within that act. And of course, earlier this year, there was the Infrastructure Act. But now you can see that through the whole society, there is so much conversation and a discussion about electrifying everything, particularly electrifying transportation. So, of course, Argonne National Lab, you will probably be sought after to help the country, solve such problems, solve such kind of challenge. So, can you share with us how do you, or Argonne National Lab, how are you approaching, for example, this challenge of electrifying transportation in this country?
Okay. So I'm going to talk about from the modeling perspective, since you mentioned the system complex. How do we get the problem right in the first place? So I'm going to talk about the energy equity you just mentioned.
That's a nice topic.
This is a recent issue that we haven't paid enough attention in the past model, right? When you, for example, when you doing this transmission expansion to expand the system, most of the time you are thinking from the cost-effective right?
Yes.
So that's whatever solution come up, give you the best, most economical solution in terms of cost saving. That's your solution. That's how you build a model. You minimize the cost, right?
Mm-hmm.
But now, being economics efficient does not mean that everybody gets equal access, right? Especially, if you consider the income disparity, like people in different region, right?
Mm-hmm.
Like for example, people tend to buy EV when they have more disposable income, right?
Mm-hmm.
And you would imagine that the people who get the EV in the first place would enjoy more. They can saving the cost on their fuel, or they can use the EV as a battery, to make money maybe in the near future. But look at the other side of this region, like people with less household income, disposable income, they don't have that privilege because of this income disparity.
Mm-hmm.
So, but the consequence is that since there's a surge of EV integration, the electricity price will change. The power consumption will cause congestion in the grid. The congestion price is shared among all the consumers. In some pattern, even like people who don't own EV, they have to pay the price. So this would be one kind of unfair, to those groups.
Mm-hmm.
So right now we are working with ISO New England, which is a power market on the East Coast, and so we're trying to see with certain percentage of with certain integration of electric vehicle, how that would impact the electricity price among different regions, and then map the price difference into the some certain income mapping, and trying to see whether certain groups are actually getting less benefit from this, and how we can address this in the for example planning. Let's see where we should build more transmission lines to influence the power flow and to change the electricity price, and eventually certain groups they are not in a big disadvantage. So that's requires how you model your for example expansion problem, right?
Mm-hmm.
Now you need to consider how we can even out this price change among different regions, which is quite tricky. People have been using like GD index,
mm-hmm.
But it has its limited. So we're currently looking at this issue and see how we can look at this complex system with not only like the power grids, but also you have a people population, with different disposable incomes, and not only cost saving, but also we want to achieve more equitable access to energy. So that's we haven't had a good solution yet. So we're in the progress identify how severe this problem could be. What are the potential solutions to that?
Wonderful. I think that's really a beautiful illustration of system complexity. Mm-hmm. So as a result, now you see that in kind of the problem you are trying to formulate, comparing to like 10 years ago, when you were doing a PhD dissertation, mm-hmm. you see the huge gap, mm-hmm. right? The jump there. And that's I think why the real world problems are so interesting. So I think you lay out that real challenge. Like if just taking power system as an example, mm-hmm. right? Of course, people always want to optimize. Mm-hmm. So actually, it's not, now you realize that it's not about how I can optimize a solution. It's really about what object function and constraints that you are trying to optimize. So, for example, this power system in response to transportation electrification, you mentioned that previously, right? You just look at cost effectiveness by minimizing cost, and you want to come up with system either operation level decisions or design level and planning level decisions, right? So it's really you're talking about cost effectiveness, or sometimes people talk about it efficiency, right? And now when you add in this equity, and all in a sudden, the formulation of the problem has changed, and even formulating the problem itself is becoming way more complicated. And so you are saying that it's still work in progress. You are trying to formulate these problems. So, do you feel optimistic or pessimistic in formulating a model for such problems?
Yeah, I think overall you need to address this problem from a different perspective. I don't think just building a model would solve the problem. You have to. I mean, this is like a system problem. You have to approach from the system perspective. Like you have to look at who are involved in the decision making, right? For example, like when you do this transmission study, like usually you have utilities, you have large customers, but for certain groups they don't have a representative in that. So maybe in the future, like even like from the procedure perspective, you could include representative from certain groups, or at least their interests are considered in this decision-making progress. I mean, from our researcher perspective, of course, we focus on methods, models, right? So that we can do, but I mean, we are not isolated in the research lab, right? So we see the problem, we see the world around, right?
Yeah.
So there are many other problems that also contribute to this. So not only you can't just like solve this equity problem by giving people equal access to energy. This is an important component, but you have a lot of other things you need to do, right? So that's why maybe we should involve like multidisciplinary people, like from social science, from economics, from environment science, all kind of people to involved to address this.
I totally agree with you. I think that's a very wonderful point, because the nature of this challenge, as you laid out, it's really systems in nature. So as a result, the solution will have to be systems in nature as well. As you mentioned, we need to have multidisciplinary teams to work on these things. And also you mentioned, at one point saying that, right, as researchers, right, we focus on methods and models. I partially agree with that. Yes, we focus on models and methods, but our goal is to generate insights. Right? It's not we don't do the models, we don't develop methods for the purpose of developing models and methods. Our purpose is to generate insights, and especially as you mentioned earlier, the importance of computational stuff. Right. So now, probably getting as you're formulating these problems, and in the end you're going to use computation method to solve those problems. So let me challenge both of us a little bit, because both of us, we are researchers, right? We love models and we love methodologies. So, and also you can say either Argonne National Lab or Cornell here, they hired us because yes, they want us to do model and the method, but also they want us to contribute to solving those complex system problems. So now I want us to build a bridge from the areas of work that we are doing in the modeling and the methods, and versus that you just mentioned this kind of complex complexity. How can our computational optimization method help those decision makers that are dealing with efficiency, that are dealing with equity? Because you can see, because the problem is so complicated, when you say yes, it's in the hand of all those social scientists, policymakers, but when they want to make decisions, what kind of quantitative foundation would they desire that on this side, computational optimizer you can provide? So instead of, given those system challenge and given the power of modern methodology and also computation, as you mentioned, what is your role? What is our role in solving these complex energy systems problems?
I think at first, as you mentioned earlier, we need to focus on the right problem. The problem, not we imagined from sitting in our office by reading paper, but also go and talk to industry practitioner. I think this is one of the benefits I get from the lab, because we are more focused on the industry, the customer. So we often go to the power sectors and talk to utilities, talk to power operators, and get the real problem. Just take one example, like one of the problems we're working on is the restoration. So how do you bring the power grids back to operation after a blackout, right? So I visited the ERCOT, this Texas power grid operator. So one of the challenges actually they mentioned that has not been mentioned before is that before they can close the switch, they need to send people to check if the segment of the transmission line are underwater or under some other situation, so that it is safe to close the switch. So if you only look at the literature, or so you will never find this critical requirement. So that has always been missing from the literature. So by interacting with the industry, you are working on the right problem that really can help the decision maker. And the other thing I think is that how you're going to disseminate your results and influence the decision maker. And that is always a challenge.
And you are right. Thank you, Dr. Qiu. And I think you made such a good point here. It's really kind of, connecting researchers to the real world, client. It's really the real world needs, right? It's kind of application driven. It's kind of researchers. Usually we are curiosity driven, but it's not enough. Right? We also need to be application driven so that to solve the problem.
So I have an additional comment. Actually, I thought about that. So as an international lab, almost every project funded by DOE, they require you to team up with an industry partner. And at the end of this project, you need to somehow you need to show this project is benefiting the industry. So I think that's probably different from the NSF funded project, where you don't have that high requirement. But for most of DOE project, you have to show how your work can benefit the industry.
Yeah, I think that's a very important. That's a very important aspect, right? I think it's kind of to. Many people mention, in academic research, there is this base value. People, you write a grant proposal, you hire a PhD or post, you work on it, and you publish a paper. You go back and write a proposal. Right? It's very rare that the research. Of course, there are good projects that that could cross, but most of they just repeat this cycle instead of crossing a value where there are technologies that can be commercialized, as you said, benefit the industry and benefit the society. Of course, they play different roles, because I'm not saying that research not crossing the death valley is not valuable. Actually, they are tremendously valuable, because they are more fundamental problems. So I agree with you. So Dr. Qiu, so kind of we talk about, especially when you are, seem like now you are in the process of helping the society to address these for example, transportation electrification while considering cost effectiveness, equity, and even kind of security, supply chain security. So with the work you have done, and also with all the insights that you have accumulated through years of your understanding about how power system operates and how power system is designed. I'm a transportation person. I do a lot of transportation research. Of course, as you can imagine, that I become easily excited about the premise of having the transportation system electrified. So now you can see in the study, people talk, we can electrify our transportation 50% by 2040 or by 2050. And people say, actually, we want to electrify our transportation. And not only electrify our transportation, we want to electrify our building sector. By what year? So I cannot help asking, can the power system support such a level of electrification of our infrastructure, for example, transportation and the building sector? So does our power system have a limit? Or is it realistic for us to aim that by a certain year we're going to electrify the transportation, by certain percentage?
Yeah, I think that's a very complicated question, and this has to be taken into the context of the decarbonization and renewable integration, right?
Yeah.
Certainly, the electrification of the transportation system created a lot of challenges. For example, you need to build the fast charging station, which is a significant challenge to the grid to manage. Of course, you have like the consumer vehicle; they can charge at home at a slower, rate, which is not too much a big issue. But with 100% of the shift to the electric vehicle, maybe that is a problem. But the thing is that we can't run the current, the grid in the future. It's not possible because the supply of the natural gas, is in disruption now, and you don't have unlimited fuel, right? So a lot of that's issue where migration to the renewable dominated power grid is inevitable, and that requires a lot of upgrade for the grid, energy storage, the DC power delivery, marine energy, a lot of things that had to be integrated into the whole picture, and this is happening while you're trying to electrify the transportation sector. So I think how much challenge the electrification of the transportation sector bring into the big picture, I think that's big. But I have to look at this problem from the whole picture where you can't run the grid with fuel anymore. Right? So that's I think that's bring a lot more complexity.
Yeah, I totally agree with you. It's a complexity, and also it's inevitably intertwined with the energy sector decarbonization. Right? It's not simply you electrify transportation. Actually, that's relatively simpler because electric vehicles can already run 500 miles, or there is no range anxiety. People are now becoming willing to buy those things. So, and then we think about energy sector and the transportation sector, and also we think about these equity issues, right? It's not going to be like many people think, we're going to, by 2040, we're going to get that level. So instead, I think it requires a very well thought out pathway design, like a roadmap design. So of course, when you think about a roadmap or pathway design, which means that we have to take steps, step by step, to achieve those goals. We will think about taking steps. actually, this is going to be related to model formulation. When you think about taking steps, it's going to be a trade-off. It's going to be a compromise, right? Which means that you are going to have to prioritize certain things, certain goals first, and then. So of course now you can see that you have coming back. You have the efficiency goal you want to maintain. You also have the equity perspective you want to take into account. So, for example, even before this point, in the previous years, right, many states, they have tried this and they had all those incentives. And the one thing is that they want to have the early adopters to kind of, spearhead the way, right? So, of course, without consideration of equity, right, as you said, kind of people probably with more disposable income, they are the early adopters that benefit from these things. Now, you said we want to incorporate this equity. When you are trying to formulate this problem, did you find that pursuing efficiency, could that be in odds to the pursuit of equity?
Yeah, I mean, in general, you would think that when the whole system is running more efficient, everyone benefits from it, right? That's true in general, but in some situation, from a certain perspective, that unfairness shows up. Like the example I just talked about, when people cannot afford EV now, so they're paying the price of expansion of the system or higher electricity. That's not fair. That's not fair. But if you from the whole society, from the global perspective, maybe that's just the price you pay as a society during the the transition of the energy, right? So yeah.
Yeah, I know this. It's a hard question, and of course, I don't want to bring us to any kind of politically sensitive topic. But I'm at the least you see that it seems like, right? It's you cannot get all the good things together. So which means that as a decision maker, actually, it's probably not. Actually, this is kind of, I think, the fun part, the easy part of researchers, right? We always say we are not decision makers. We provide tools and we quantify all those different outcomes of all those different scenarios, and we leave the difficult problem to the decision makers, right? They can choose, because they can choose a compromise between, or the trade-off between equity versus efficiency, right? Those things. So yeah, but actually that comes back. I think our role is really right. We try to provide the best science and the best supporting numbers. And apparently for this energy transition, it's multi-objective. It's not a single objective. And we all know that when you come to multi-objective decision making, it's really the decision makers, what they have to prioritize, right? But at least as researchers, we provide them with all these numbers, all this data. So I think, Dr. Qiu, we talked a lot about this complexity, and I believe if the audience watch your conversation, they probably agree with you that wow, it's really complicated. So and they want to ask, okay, how can we solve these complicated problems? And then probably the answer is that okay, we should have more of people like Dr. Qiu, who not only has all these analytical, very, very, solidly trained analytical optimization, computational skills. He also, through his decades of development, he also has the appreciation of all other social aspects in doing these things. So this can lead me to, I think, our towards the end of our conversation, my question would be, how or what Cornell System Engineering Program should do, and how can we, set up our education system such that we train future researchers, leaders, and engineers that are ready to cope with the challenge that you just laid out. Because as you and I, we agree that the traditional departments, the product, the graduates from the traditional departments, they are not necessarily ready to cope with all these system challenges. And even for you, like you graduated from the top system industrial system engineering program, and I bet that when you went to Argonne, you might solve the challenge because you were trained as a specialist, but you were addressing, you were attacking the system challenge. So now what I'm trying to say is that Cornell system engineering programs, we are established to educate system engineers that can better address the system challenge. So what would be your advice as a person who kind of walks the talk? What would be your advice for us? And not only for Cornell system engineering program, probably for our education sector as a whole. Mm-hmm. How can we train and produce students in the future workforce that are better suited to addressing the challenges that you have laid out?
Okay. Yeah, I think that my understanding is still shallow. So I don't think I'm well qualified to give this the answer. But I can make some suggestions from my own experience.
Thank you.
So I'm sure Cornell has a lot of excellent people, educators, that they can pass good knowledge to students, tell students how to do things. But one thing I think would be beneficial is that to get involved in real work. For example, doing some internship at the early stage of the education program, and trying to understand how complicated the real problem is, mm-hmm. and get perspective from other domain. And I think that would be even you don't come up with a solution, even you don't learn something, at least your perspective will be changed, your attitude will change, because you see how complicated the problem is, and you have to take a systematic approach, not just using what you know to do things, but you have to look around and see what other problem might be related to this, and how. So I think like for example the internship program at Argonne or at other national labs provide such an opportunity, mm-hmm. To look at real problem in the energy domain. So I think I highly encourage students from your program to look at the internship program at Argonne and other national labs and consider as a way to know the real world.
Dr. Qiu, I think that's such a wonderful point, and I think you while you pointed directly to a real action of developing internship program, mm-hmm. and I feel what you are really pointing to, and which is so important for education, is that early on in the development of students, set up the right mindset.
Yeah, mindset.
I think a mindset is so important, such that I feel that's what an intern can help them, right? Achieve that, to set up the right mindset, such that through the internship or through other experience, and they come back to the program with a purpose.
Yeah.
And
open-minded.
Yes. Yeah. I think that's really important. And also, thank you for sharing the information about the internship opportunities at Argonne National Lab. Do you want to share more information about the specific opportunities?
Yeah. So actually, the Department of Energy has an undergraduate intern program. They have 2 terms per year. So I highly encourage the student from your department to look at this program and apply. And you have I think dozens of national labs you can choose in different majors. That would be. I'll send you the link.
Yes, please. Yeah, and please make sure in your seminar talk.
Okay.
You can also mention this, because our students, they will be attending your seminar talk.
Okay.
Yeah.
Sure.
Yeah, Dr. Qiu, I think I know that you have a talk later on about machine learning, enhanced machine learning, especially in the context optimization, for example, for mixed integer programming. of course, I don't want to pry too much into your talk because, right, you're going to talk about it later. But I feel probably if you want to mention a few things about what your talk is about, because that way, people, if they happen to watch this video, they will know, oh, actually, Dr. Qiu has another talk that can lead them to that talk.
Okay, sure.
Yeah.
So basically, when we are facing an optimization problem, normally people think about it from mathematical approach, right? How do you derive the decomposition algorithm? How do you derive the cutting plans, from So, but people usually ignore the context of the problem. So the most of the problem in real application, they are solved repeatedly. And this problem shares a great similarity. So basically, you are watching a problem solved again, and again. And now you are thinking about very naturally. You can use machine learning to gain and learn, develop better strategy to solve it. So basically, you are trying to develop an artificial intelligence problem solver for that particular problem. And so I will talk about how we could achieve this to help you to solve your optimization application faster and faster.
That's beautiful. It's basically you're talking about taking advantage of the past.
Yeah.
Right, and that's exactly kind of the nature of learning. So when you talk about that, learning from the past, and then or like in Bayesian, it's kind of from the prior, and then go to the posterior, going from the prior to the posterior. So in this learning thing, of course, we can learn from our own past. An algorithm, it can learn from its own past. How about cross-learning?
Cross-learning. Cool.
So, for example, each machine learning algorithm is kind of like you have this kind of streamed data fed in, and then you learn and you use it in solving field problem. And of course, there are also other algorithms. Think of each algorithm, think of each machine learning tool is as an individual. We always I don't know if you have children, I have children, I will say that, we say, smart people, they learn from mistakes. And we say, smarter people learn from other people's mistakes instead from your own mistakes. So what I'm trying to say is that you're not only learning from this past, solving this problem, and also learning from the past of other problem, other solvers. So that's what I mean by cross-learning.
Okay. In addition to learn from the past, we also predict the future scenarios. And we learn from the future scenarios, which are solved, immediately, and learn from those relevant scenarios could get more insight about. But of course, you can develop multiple, learning model, right? So that we do usually in comparison, we compare which performance is better, and then we choose the best performer. But I think that you bring up a good point. How can we learn from others? So we haven't thought about that yet.
Okay, wonderful. I think our time is up, and Dr. Qiu, it was a great pleasure to talk to you.
And my pleasure too.